This paper is called Elaborating on Learned Demonstrations with Temporal Logic Specifications. The motivation behind the work is this. Teaching a robot via physical demonstrations is a pretty well established method of learning complex manipulation. But we mostly assume that the demonstrations alone contain enough information to learn the underlying task. If you think about it, this is often untrue for at least two reasons. The first reason is that the demonstrations might just be poor quality. Imagine pouring a cup via teleoperation. We might wobble, miss, or spill something. Here's the second reason. The task might have underlying specifications, which are simple to express verbally, but would take loads of data to learn from demonstrations alone. Again, in the pouring example, think about trying to learn the rule, don't tip the cup over a certain number of degrees until it's over the bowl. Ideally, we want to convey the core movement information with a demonstration, but we also want to elaborate on precise task details with a specification language. Fortunately, the robot verification community already has a formal language for common temporal constraints, and that's linear temporal logic. Here's the cup pouring rule in LTL. It says, at all points in time, if you're too far from the bowl, keep steady. In this paper, we transform LTL into a differentiable loss function and combine learning from demonstration and LTL constraint satisfaction into a single connected learning process. Let's first take a look at a standard learning from demonstration pipeline. Your inputs are generally like a scene image and a robot starting pose. These inputs are then fed into a feed-forward neural network, and your output is parameters of a robot trajectory. We train this by feeding it pairs of inputs along with demonstrated trajectories, and then adjust the neural network parameters to minimize a loss. This loss is typically the difference between the generated trajectories and the demonstrated ones. What we add to that is an additional loss term based on how strongly the generated trajectory violates some user-specified LTL constraint, the phi term here. To do this, we need to convert this logical formulation into a differentiable loss metric. You can see the full details of this conversion in the paper. With this system, we actually did the pouring task exam from earlier. We got a PR2 robot, cup and container, then demonstrated pours with an HTC Vive. It turns out to be difficult to pour things when you're moving someone else's arms, so we ended up spilling stuff in most of the demonstrations. But now, we could take those poor demonstrations and combine them with our keep steady specification. You can see our final blue trajectory maintains the overall shape of the original demonstration, but makes minor adjustments to successfully avoid spills. Now this works great for augmenting a single demonstration with an additional specification. But what about learning a generalized behavior from a batch of demonstrations? So far, we've only really learned to satisfy the constraint for the training input. What we really want is to say that we can satisfy the constraint for all feasible inputs in some domain. To achieve this, we have a two-phase adversarial training loop. In an inner loop, an adversary searches for an input which violates our spec. Then, in an outer loop, our network updates its parameters to try and satisfy this adversarial counterexample. And we repeat this until convergence. With this training framework, we can build complex movements from a batch of demonstrations combined with an LTL spec. In this one, our blue learn trajectory is learning to satisfy a combination of constraints shown in red. So in this work, we've taken a standard learning from demonstration system and combined it with a quantitative semantics for LTL specifications. We can then elaborate on a single demonstration or a batch of them using adversarial training techniques.